All right, welcome back. This lecture begins the first set of lectures on applications. We're going to talk about today about computer vision. We'll talk about that today and next lecture on Wednesday. Then we'll go through some other applications, things like scheduling, robotics, and natural language processing, and then computational game theory, briefly. Before I get into the material here, there's a couple announcements. Homework 3 is posted now on the website. I believe that the auto lab aren't quite up yet, but they will be up shortly, like today. Yeah, by 5 today. So unless someone really wants to submit, next 2 hours, probably be okay. And the last thing is that we do have the midterms ready and graded, and we'll hand them back at the end of class today. I'll actually spend the last 20 minutes or so of class today handing them back and then going over some of the problems that were the trickier ones, as well as talk about I'll let everyone know what the mean and what the standard deviation was and all those kind of things, and you can ask questions if you feel that some of them were not quite intelligible. All right, so and then I guess the solutions we're also going to post for they're not up now, but they will be up today. Yeah, okay. All right, so before I jump into it, though, is there any questions, either on the general course topics? I guess we're also going to soon post information about the final presentations and posters, but that will come this week, probably. Are there any questions sort of about general topics now? All right, well, in that case, let's jump into computer vision. This will be a fun lecture because I'm going to try to intersperse it with some demos through the lecture, so we'll see if that actually works. They're video demos, so it's always a question about whether the lighting in here will actually jive with that. So we'll see. All right, so let's jump into computer vision. These 4 topics are going to be kind of, as everything else in this course is to a certain extent, I guess, but it's going to be very, very quick introductions to these different topics. So this is computer vision. There's 2 lectures on it. There are, I think, a whole series of courses on computer vision at CMU here. So you can certainly go into this in a lot more detail. But the goal here is to cover just some of the basics, as well as give you a little bit of experience with some hands-on implementation of these things. So in particular, I'm going to talk about first some basics of computer images. What is an image in a computer? How is it stored? This is probably all old hat to everyone here because you already did it in the digits project. That was a way of storing images on a computer. So, and if you hadn't seen it before, you probably had seen it before too, even if you hadn't. And if you hadn't seen it before, you saw it then. So this will be pretty short. The majority of the time I'll spend today on image processing. And actually, these next 2 image features and object recognition, they're not in the slides yet. They're going to be talked about on Wednesday. So I'm going to spend most of the time talking about image processing. And these are things like, how do we take images and apply some transformations to somehow put them in a form which is more useful for whatever we want to do, right? And that's very vague what I'm saying right there. But the overall goal of computer vision is to somehow understand what we see in images. And these are going to be some kind of basic, fundamental manipulations we can do in images that make them more readily, make them easier for us to run algorithms which actually get to that understanding. Hopefully that'll make a little more sense when I actually describe what we're doing there. But before I get to that, let me jump in and talk about basics of computer images. As I say, this is probably going to be a review for everyone, but we have a few slides here just describing what an image is on a computer. So probably you've seen this before, but basically, if you look at an image, you can immediately identify certain things in that image, right? There's a person here. He is looking through a camera. There's some background. There's a sky here and some grass there. And to do all that was actually amazing. The fact that you were able to immediately look at this and tell all that, right? Because that's a huge amount of information there that is very non-obvious from what is actually encoded in this image here. What the computer sees is just a list of pixel values that describe this image, right, in a big matrix. So I'm just showing here down the top 4. This is just this little left-hand corner up here. But still, I mean, I guess you wouldn't get much information if you just saw this anyway. But still, all the computer sees is a bunch of these things for every pixel in the image. And it's very non-obvious how we can go from things like this representation to actually some description like I gave before about there's a person here looking through a camera. Behind him are buildings, skies, and grass. That's a very complex description, a complex task there. And we're not going to really necessarily talk about all that today or even in these lectures. Going from sort of this image to a story about this image is kind of one of the grand challenges of computer vision. But what we will do is talk about how we can process images like this to maybe make this job a little bit easier for a computer. And then next time we'll talk about how can we do some basic tasks like recognize, very basic objects in here, do things like detect important features in this image and stuff like this. That's what we're going to sort of limit ourselves to in these two lectures here. Now, for color images, as you might also imagine, it's the same thing. There's just 3 different images, one for the red, green, and blue component of the image. And we should say that I'm going to focus today almost exclusively on grayscale images. This is very common in computer vision because a lot of things are a little bit more naturally defined when we talk about grayscale images, only having 1 image instead of 3 images. But you can apply most of these techniques to color images, either by applying it individually to each channel or just by actually looking at slight generalizations of these things that actually apply to color images natively. And finally, when I write images throughout this lecture here, I'll typically think of image pixels as being real valued entries, namely usually between 0 and 1, right? So 0 being a black pixel and 1 being a white pixel. But of course, when we actually represent them in a computer, they'll typically be like an 8-bit value or something like that. So just these are sort of minor points here, but I just wanted to set the stage for what we're going to do. And then finally, I don't think I can really, in this lecture, give that much useful information in terms of letting you go on and sort of do image processing. But one of the things I can do, which actually gets to that, will be to describe, rather than just sort of give you the math about how to do manipulations, to also describe how you code some of those things up using what's now a pretty common and standard open source framework called OpenCV. OpenCV is a set of routines and libraries that are built for computer vision. CV here stands for computer vision. And they're fairly standard. So what's nice about them is they let you do a lot of the manipulations that we're going to talk about in a very easy way, with usually just one call to a library or something like that. And we'll also kind of show what these things actually look like. I'll demo some of that on my computer, and hopefully that'll all work. We'll see if we'll see. That's always a risky thing to do in front of a live audience. So we'll try to get through all that. But essentially, what this boils down to is that I'm going to end up skipping over some details about how you actually implement certain algorithms. But I will point to you to an implementation of how you actually do this and code that can actually do it if you, in fact, want to go deploy these algorithms, right? And I think this is actually a similar concept to what we did when we talked about optimization. Like optimization, computer vision is a pretty well-established set of methods at this point. And so it's actually, in some ways, a lot better to just kind of learn the basic idea and then learn where you can find them, rather than spending all your time implementing like a canny edge detector and all this kind of stuff. They already exist. They're already very well implemented. Just go use it. So, having said that, here is how you use OpenCV. OpenCV is a library that has both C++ and Python bindings. So that's nice for us because we're going to use Python here. We're still trying to decide, actually, if we are going to give you this on your homework or not. It took me a few tries to install OpenCV on Python on my computer, so that's a little bit nerve-wracking. But hopefully it isn't too bad. It's just you have to learn how to do it right. So we're going to try to do some of this for the actual homework next time, for the programming project of the next homework. Not homework 3, but the homework 4. But that's still sort of up in the air. But even if you don't have it on your homework, it's still an incredibly useful library to use. So I would recommend everyone, especially if you want to do any computer vision, to go download it and try to actually use it. So you can do things like this. So basically, OpenCV has an interface to Python called CV2. So you can import it like you import anything else. And you can do things sort of very, very easily, like read a PNG file as a grayscale image. So this reads that camera image as a grayscale image and returns it in this image item. An image here is actually just like everything else in Python. It's just a NumPy array. So you can access certain elements of this thing just as you would any NumPy array, and actually also run any kind of averaging or any other kind of command you would on any other array on this image directly. You can also write to images, so you can save your images, especially if you do some manipulations. You might want to save those things. You can also show it on the screen, wait for some input, wait for the user to cancel it, etc. So it's very nice. If you were to have to do this manually, you'd have to write an actual parser for the PNG format, which is, you could find one, but you have to probably download like libpng or something like that. Figure out how to use it, figure out how to load these files. It's kind of a pain. And so this set of libraries makes it really easy to kind of do this kind of stuff and quickly be able to actually do the manipulations that you want to do with things like videos and images. And in fact, you can also do things like import video from a camera. So this is what I'm going to try to do right now, and we'll see if it actually works. It's not very interesting right here because I'm just displaying my webcam, which is not that exciting at this point. But when I do later algorithms, hopefully it'll be kind of cool to see these things done in actual real time rather than just sort of seeing them in the pictures themselves. So let me give this a shot. If it doesn't work now, then we will abandon it and move on from there. But I don't even have the right command loaded in this new window. But let's see if this works. OK, here I am. There. I'm even handling the infinite recursion there pretty well. OK, so that'll be fun when I start starting all this image processing. But not too much here. It's a picture of me. You can already see me in the. I can still see me many times when you watch the video of this. But that's actually pretty nice, pretty good response here, right? And what's actually very cool is this. You will be able to see how fast some of these algorithms are because we'll be able to apply a lot of this in real time. So that's all for now, but we'll get back to this shortly. And the commands for this are just you open a capture with this command video capture, you loop forever, you get the return value in the frame from the current camera, you show it, and then you wait until you press any key to quit. All right, so pretty straightforward there. It's really nice, though. If you ever try to read data from a camera without these things, sort of directly from the actual raw data streams in a camera, it is really annoying. So this is a really nice kind of framework to be able to use here. All right, let's now talk about what we actually want to do with images, which is process them in some manner or another. And here I'll talk about many things. I'm going to talk about first converting, the simplest one, which is still interesting in some sense, but it is very simple, is how we go from that image there, which was a color image, to a grayscale image, right? Because we want to do manipulations in grayscale. How do we convert from one to the other? I bet you can probably guess how to do it, but you probably can't guess how it really is done in practice, unless you've actually done it before. Then we'll talk about convolutions. Convolutions are actually form the basis of how we do most operations in practice on images. So it's important to understand convolutions and how you apply these things and sort of intuitively what they actually are. And then we'll talk about image gradients and edge detection. And that'll be all we talk about today, but we'll cover those three things. So let's jump in first to grayscale. Now, the basic premise here is not very complicated. The images that I get out of that camera there are RGB images, meaning they have a separate channel for each red, green, and blue separate image for each red, green, and blue component of every pixel in the image. And what we want, because that's kind of complicated to work with actually in a lot of ways, is we want to just convert that to a grayscale image. Okay? And now it's not very hard to do this, as you might imagine, right? A simple thing to do would just be to take these three images. I'm treating these images here kind of, you can think of these as matrices, right? These are each a matrix that is the size of the image you care about. They each have values from 0 to 1 that describe the intensity of that color in that image. And the obvious thing to do here to convert to grayscale is, well, you take the red, green, and blue components, you add them up, and you take the average of them. That is your grayscale image. And I'm using Y here to denote my grayscale image. Now, that is very, very simple. And it's not what any software will do when you convert from RGB to grayscale. There are actually better ways that just more, to the human eye, look much more pleasing. And so there are a couple things you can do. One is called a lightness. So basically, it takes the maximum of these things plus the minimum, leaves out the middle one, and divides by 2. But the most common by far is something called luminosity. And this relies on the fact that certain colors by the human eye register more with brightness than other colors. So in particular, we're very sensitive to green colors. And so if an image has very high green colors, you want to make the brightness much more than if it has low green colors. In contrast, we see blue colors actually being kind of like darkness. We see blue as being actually very similar to black. And so you don't weight the blue component very heavily here. This seems a little bit odd here. And where do these numbers come from? Well, they actually are just kind of tweaked, right? These things aren't set in stone anywhere. They're kind of someone's interpretation. This actually is what GIMP does. GIMP is the GNU image manipulation program. This is the weight that GIMP uses when you convert from color to grayscale. But OpenCV actually uses a slightly different set of weights here. So there's no exact science here. This is kind of fiddling with things until they look like something that is pleasing to the human eye. So I'll show them here. It's unfortunately not the best display for doing this. But here is also an example from the GIMP documentation where they have a sunflower image here. You have the grayscale thing you get out of averaging, out of the lightness operator, and then out of luminosity. And I guess all you're really going to see on this projector here is that the luminosity one, these look a little bit brighter. And you can kind of see, if you just sort of look at this, it seems like this one kind of captures the lightness of that sunflower a little bit better than the other two, than the other two do, right? And that's because being yellow like that, we actually register it as being a fairly bright color, even though the intensity isn't as high, or is not that much higher than other places in the image. Because it's yellow and yellow has a large green component, we view it as being a bright image. Now, you can also do this in OpenCV. So easy just to convert. The command is CVT color. You input your frame, which is our frame from video, and you output the color, second argument is the color space you want to do conversions from and to. So this is going to convert from BGR to grayscale. It's actually the case that most images are actually coded raw off the camera in terms of their blue, green, red components rather than RGB, even though we all call it RGB. I don't know why that is, but it is the case. And again, this is using the luminosity transform with a slightly different set of weights here. Yeah?
Has anybody ever gone through different luminosity weights and seen
how people react to those?
How well they work with different computer vision algorithms?
I don't know if that's the case. I think that if you have color images, and you really want to get the best performance possible, it is good to use the color information. So I don't know if people have sort of trained luminosity to optimize computer vision performance. My guess is it would have a fairly small effect because most of the information is still kept there. And so even if it isn't as pleasing to human eyes, to a computer analyzing it, it would still be just fine. So it's sort of because we see things like this, we do it this way. But it isn't usually, the computer could figure it out either way. That's sort of a guess there. I don't actually know. So maybe I'll just show this then. Since we're doing this, this is a quick one. But I can also, for example, bring up a nice grayscale image of myself. This is the exact same thing. I just ran that command that said CVT color and then BGR to gray. All right. All right, now let's talk about the kind of basis for a lot of the operations we're going to do in computer vision. And these are convolutions. And a convolution is written like the following. We have some matrix Y, which is our image here. And Y in general throughout this lecture will just be some arbitrary image, which I'll say is M rows and N columns. So Y is going to be some image here. And it will typically have values between 0 and 1, corresponding to the brightness of the pixel. Now, actually, Y, especially when you apply operations, can have values afterwards that are lower than 0 or bigger than 1. Sometimes naturally. Sometimes when you compute things like the gradient, it's actually very natural to have negative values. Those make sense here. But sometimes even after you do interesting things in filtering, you will still get some components that are either over 1 or less than 1, etc. And so in that case, we still think of it as a matrix. We can have values that are over 1 less than 1, but when we actually display it, we would just clip those values to their appropriate range. But it's important to know that these things can, if it's a raw image, we think of it as having values between 0 and 1, but it can have, depending on what we do with it, it can have other values as well. So a convolution, which is written like this. A convolution is written like some matrix star y. And what that is that says, let's take this matrix here. And I'll have an animation of this in a second, but I'm just trying to get the intuition here. Let's take this matrix here, and let's kind of slide it over all possible positions it could be in that image there. We take the product of all the corresponding entries, and we add them all up. And that gives us a pixel in a new image. So let me show you what I actually mean by that, because it's a little bit confusing. Here's an example of convolution. So here I'm going to say that this matrix convolved with this one equals this one. Sizes here actually are important, though I'll talk about this in a second about this is what you usually will see in actual computer vision. Usually you will see the final image being the same size as the original image, but I'll address that in a second. What convolutions do here is we have some matrix H, and I'm convolving now H with Y. Where's my eraser? So here what I'm writing is a matrix H, which in this case is 3 by 3, convolved with a matrix Y, which is in this case 5 by 5. And what you do here is you take the entire matrix H and you slide it over all possible positions it could be in the matrix Y. All right, so you take it here, you first look at this corresponding 3 by 3 block. If you take all the corresponding elements here and multiply them together, so you have h11 times y11, h12 times y12, etc., h22 times y22, 33 times y33. You add those all up, that gives you the first element in the solution. Okay, similarly, you then move this whole thing one space to the right there. And the similar corresponding entries here give you, add it all together, give you the second entry in the convolved image. Right, so this thing times this thing, h11 times y12, h12 times y13, etc. Sum those, take the product of all those, sum them all up, and you have z12. Has everyone seen convolutions before? Who here has seen these before? Okay. So you can define them in terms of sums as well. The notation is actually pretty simple, right? It would just be essentially the sum over all these things times sum over all those things. It gives you this one here. But I'm just going to sort of say it informally like that, and hopefully that conveys what's actually going on here. If it doesn't, actually someone speak up, because hopefully that makes sense to everyone what's going on. It's a very simple operation. You just take take this block here, slide it over all possible positions, and then take the product and add them up. Okay. Now, in general, jumped a little bit there. In general, people actually typically do this a little bit differently, such that the output image is the same size as the original image here. It's a little more convenient if it doesn't shrink every time you apply another convolution. That kind of gets annoying quickly. And all that really people do then is that essentially for the corners, or sorry, for all the borders, they'll have a slightly different convolution. So maybe in some cases, when you have this, let's see. So if you have your 5 by 5, and you want to create another 5 by 5 matrix here, you want to look at this sort of first entry. You would take maybe these 4 pixels here, and take only of your convolution image, you take only these ones here, and you would scale them appropriately to make it all work out nicely. There's no well-defined methods to do that at the borders, but there's lots of heuristics because it is just nicer to have images that are all the same size. This is a minor point. Doesn't really get to the majority of it. It's kind of an edge case, literally, on the borders there. But it is just sort of good to know that that's actually what's happening, so that when you convolve an image in OpenCV, just know that it is doing something behind the scenes to make sure the images are the same size. And finally, in computer vision, you typically will see odd-sized convolution matrices. We'll also call these sometimes filters or sometimes kernels. I try not to use kernels because that's also a term in machine learning and a lot of other domains here. So I'll try to use something like a filter. So we'll try to use odd-sized filters. That is odd as opposed to even. Because if they're even, then there isn't really any pixel at the center of the convolution, right? So it sort of doesn't really correspond to any, a pixel here, this pixel here, in some sense corresponds to this pixel here, right? Because this is the center of the convolution. Similarly, this one here will correspond to this one here. But if you don't do that, if you have them be even, then kind of it's sort of the center. It kind of corresponds to like the center of an image, which is kind of strange. So those are all very informal things. Just they're kind of typically what people do when they talk about convolutions. And when they use convolutions in practice. I think actually some of the routines that you use will actually throw an error if they are given a non-odd-sized filter. Yes?
How do you do the size of the window?
Yes, that's a great question. Because you could just choose it to be like, 1 by 1 and have a one entry. That wouldn't be very interesting, right? That would just create the exact same image. The size of the convolution depends entirely on what you are trying to do with it, right? This is just an operation. What you actually want to accomplish with this, which we'll talk about now, is, why is this useful? What are you trying to do when you actually do a convolution here? And depending on what you want to do, you may want bigger or smaller windows. Informally, what this is saying is that if you have a bigger window, then this output pixel here depends on a whole lot of input pixels. So if you're going to do things like blur the image, you could, for example, blur it very heavily if you have a very big window. Whereas if you have a small window, you can't blur it that much because you can't really do that much. With the, you have to only depend on a small number of pixels in the input. Maybe I can actually show what those actually look like in the demo. But hopefully that will make a little bit more sense when we talk about what we actually do with convolutions rather than just the definition of convolution. All right, so what are some normal convolutions then? One very common one is making the pixel in the output, or it's like this, making each pixel in Z be an average of some pixels in the original image Y. Right, so if I convolve an image with this matrix here, the all ones matrix, divided by 9, then each output pixel here is just the average of those 9 pixels there. Right? So you think this is kind of like a blurring operation, right? Because you're taking the image, which has a lot of information, and you're kind of throwing a lot of it out. You're making everything be the average of all the other pixels, or not all the other pixels, of some number of pixels in the original image. This is very common, but it's actually also not, if your goal is to do something like blur the image, it can actually be a remove noise from the image, something like this. It actually can be kind of not the best thing because it treats every pixel in that window equally. A more common thing to do is actually to use what's called a Gaussian blur, which is just like the one we saw before, but these entries of your convolution filter are actually entries from a Gaussian distribution here. And so if you've seen this before, essentially what this will look like is that the center one will be equal to 1, normalized by something there. And this one will be equal to something, well, it'll look like this, right? It'll look like an image like this where each sort of bad drawing, hang on. I guess I wasn't actually drawing level sets there. So if you think of this in 1D, what this would be doing is this would be looking like a Gaussian distribution, right? And so each entry of your filter is some position on this distribution. So it's like these, say those 5 points there. So if you have a 5 by 5 Gaussian blur filter, that would be essentially this thing, but in 2D, where this is kind of a spherical Gaussian. Now, the best way to think about these things is really just to see what they look like, though, because what they actually, mathematically are is interesting, but not that interesting. And so what's really sort of the way you get intuition with these things is actually just trying them out. So, for example, here is a averaging convolution applied to this image here. It's a 5 by 5, so it's like a 5 by 5 matrix here. That would be 1 over 25 times the 5 by 5 matrix of all ones. Convolved with this image here looks like this. And unfortunately, it's kind of hard to see exactly here, but it looks much more blurred out. But there is also some sort of little edges here that are kind of a little bit like artifacts. Because essentially, when you do things like average all the pixels in this camera together, you get some averaging between things that have no real reason to be averaged together. Like why would you want to combine this pixel here with that pixel there? I don't really know. And so it's not very obvious here, but if you look in the actual slides themselves, you'll see this a little bit kind of there's some odd stuff going on right here. Again, not really visible at all in the projection. Whereas this one, which is a Gaussian blur, which looks, I think, for our purposes, the exact same on this display here. This one and the actual slides will look much more like what you typically see of a blurred image. The Gaussian filter typically, because it doesn't put too much weight on the outsides here, right? It puts a lower weight on the outsides. You get a smoother kind of blur than you would with a normal blur. So maybe if I try it, we can actually see this. I'll give it a shot. So here is I think just call it convolve. Here's a blurred picture of me, and this is a picture that is blurred with a, I think, 15 by 15 image. Sorry, 15 by 15 all ones matrix is blurring this image. And I'm trying to see if you can see some odd artifacts here. And it looks like I think that this projector does a really good job of actually blurring my blurred image. So you don't see it at all, but you can maybe hallucinate that you do see a little difference here. I can see a great difference on my screen. But then let's show the Gaussian one just for the sake of argument. I think I actually didn't. That one was not blurred as much though. Let me make this a little bigger, 20 by 20. Oh, that's right. So this is actually, I made it 20 by 20, and it actually threw an error, because they have to be odd sized for this thing. So 21 by 21. All right, and this, again, if you try this out on your own, it looks much, much smoother, I promise you. Looks about the same on the actual display. Oh well. Hopefully the next ones with the actual gradients will go a little better. So in some sense, this is kind of the most obvious sort of operation you could do, right? And it isn't that interesting because you're just sort of taking an image and kind of throwing away most of the information. Why would that actually be useful? It turns out that blurring is actually one of the more useful pre-processing steps you can do with images, because I can still tell what's going on in that image, right? And by doing this, I'm actually removing a lot of the noise in the image, the sort of a camera just puts in when it takes a picture. This one isn't too bad, but some pictures are sort of very obviously very noisy. And blurring it a little bit actually removes a lot of the noise and makes it much easier to process the image for future computer vision algorithms. So, as I said, here's the code. OpenCV has code for both general convolution, so the filter 2D function will perform a general convolution of an image. It also has built-in methods for blurring and for the Gaussian blur. So if you just want to do those, you can just call blur or Gaussian blur and blur your image that way. All right. Now let's talk about something a little bit further afield. And this is an aside. We're not going to do this at all in this course, but people might have heard of this. And so it's good to sort of bring it up and where it fits in everything. And this is something called the Fourier transform. So the Fourier transform is a representation of images in essentially what amounts to frequency space. So if you've not seen before, I'm not going to define any of this. This is very, very hand-wavy right here. But essentially, you can represent any image in terms of what frequencies, what sort of sine waves, what sum of sine waves are active in that image. And you can represent any image as a sum of lots of sine waves. In fact, if you have enough of those sums of sine waves, you can recreate any image perfectly. And so it turns out that there's a very sort of nice way of doing things that lets you very quickly determine the frequency representation of an image. And this is called the fast Fourier transform. What I'm showing on the right is the fast Fourier transform for this image here. And it is not very meaningful if you look at it, right? It's actually, I'm showing the magnitude to the fast Fourier transform. The Fourier transform is actually a complex quantity. It has a real and imaginary component. I'm showing just the magnitude of that thing and taking the log of that too to kind of show off the different features here. But essentially what this boils down to is that this image, though it does not look like it, encodes all the information in this image. So you can move between these two things by what's called the Fourier transform to go from here to here, and the inverse Fourier transform to go from here to here. Okay, now that does not seem very useful yet. But the reason why this is useful is that it turns out, and I will not prove this, or even talk about this after this slide, it turns out that this operation of convolution here, convolution, convolving two images together, is the same thing as multiplying them together point-wise in frequency space. So if I take the Fourier transform of this image and the Fourier transform of a great big Gaussian blurring kernel, this is one I would have to do a lot of operations to make every pixel, right? Because I have to sort of take a great big Gaussian blur here, compute every single possible product, sum them all up, then move it over one pixel and do the same thing again. It's a lot of operations. What I can do instead is convert to the Fourier domain both the images, the Gaussian blur and the original image, and just multiply each pixel, you call these pixels, multiply each pixel together, apply the inverse transform, and that actually is exactly the same thing as the two images convolved. Mathematically, they are identical, and numerically, with a good implementation, they will be identical as well. So that seems great, right? Because this convolution, I mean, it seems like this is actually kind of a lot of work here. If we have to every time, take every single element here, multiply all those elements, etc., that seems like a lot of work. The Fourier transform gets around that, and actually, it turns out that you can convert between this image and that image in the number of pixels. That's sort of obvious. You have to pay that cost. But then the number of pixels times the log of the number of pixels is all it takes to convert from here to here. And so if your filter size is a lot smaller than the log of the number of pixels, you're actually better off doing this conversion, doing convolution in the Fourier space, and then converting back. This was all kind of an aside. If you have seen this before or heard about this before, this is sort of where this fits in. I feel like I couldn't mention convolution without mentioning the fact that there exists this efficient way of doing it. But the reality is, for small convolution operations, which is a lot of what we do in computer vision. A lot of computer vision is about kind of small little things to detect things like edges or detect changes and sharp changes in intensity. Those things can all work just doing the convolutions directly. You actually don't end up doing better by using a Fourier transform. It just ends up taking more time to convert from one to the other. So,
what do you mean by multiplying a 3x3 filter by a n by n image?
Yeah. So what do I mean by that?
Yeah.
Is that the question? Right. So this is the image to have here. If I want to multiply, or if I want to convolve this filter with this image, for each output pixel, I have to do 9 operations, right? And if my filter is 25 by 25, each output pixel costs 25 operations. In the Fourier space, to do a convolution, I just multiply things together. So I take the convolution of this, and actually I have to pad it a little bit and do all these kind of tricks to make it kind of nice. I have to do a Fourier transform of this and this to make them the same size. Then I just multiply together corresponding elements. I just take the h11 and multiply it by y11, etc. Or the tilde, y11 tilde, which tilde is the Fourier transform.
Both the filter and the image will become the same size after the convolution.
Yes, actually, well, not after the convolution. After the Fourier transform, what you do is you first pad this with extra zeros, essentially, to make it, because that's the same, right? If I make these, put extra zeros here, it doesn't matter. It's all the same. It's just if I handle edge cases correctly. So I pad it with extra zeros. I convert them both to the Fourier domain. I multiply them together. I convert it back. That's sort of what has accomplished this. And it's just a matter of sort of doing all that math to get to that point. But it's intuitively, it seems like fewer operations, because you don't have to do the however many elements there are here for each pixel of the output image.
So if you pad it with zeros, isn't that going to give an extra edge and a sort of
you have to be very careful when you pad with zeros to handle this correctly. But if you do it correctly, it's exactly the same. Because zeros won't, right? Zeros just won't affect things. If you handle, depending on how you handle edges, a zero here will not actually affect your output at all, right? Because you're summing them together. So you can zero pad, and it isn't a problem. Assuming you normalize everything correctly. Yeah. All right, so that's all I'm going to say about the Fourier transform. Can be a very nice trick when you have very large filters you want to apply. But for the most part, we're going to talk about kind of smaller filters. And in that case, just do it directly. Don't worry about the Fourier transform. Ends up taking more time. All right, so let's just finally, and we'll have, hopefully it's been like 20 minutes or less on this, so we have plenty of time for the midterm. I want to talk about image gradients. Now, the motivation here is that edges in an image are kind of, they represent one of the more important characteristics we could think of in this image, right? So if you look at this image, how do you know what's going on in there? It's probably not because you sort of could read this guy's coat and figure out what was going on in his coat. This was the person, right? You probably saw the outline of the person, saw places where the image changed very rapidly in its brightness, and use that information to figure out what was happening there. So intuitively, we gain a huge amount of information from these edges. That's sort of where we really can interpret things. And in fact, I could show you an image just like this. It was kind of a line drawing, and we'll show you that in a second, where you could probably get all the exact same information out of it, have much less real information here, right? It's just mostly black, but a few lines. You could probably tell it was still a person looking through a camera, etc. So extracting edges is in some sense kind of one of the first things we might want to do if we want to talk about understanding an image. So how do we go about doing that? And intuitively, what we sort of think of as an edge is, well, an edge is a place where the intensity of the pixels changes very quickly. Right? We don't call these here edges because the pixel values are all kind of the same here. In contrast, we would call this an edge here because on this side it's sort of gray and this side is black. I would call the same thing, this is an edge here because this side is white and this side it's black. And even the grass is kind of tough, right? Because the grass, there is some sort of texture here, but at the same time, it's kind of a little bit washed out. Maybe if you blurred the image a little bit, you would not be able to even tell there was any texture there. And so all these things kind of have to be taken into account when you want to think about what is an actual edge in an image. So the way we're going to define this formally is through a notion called the gradient of an image. And the gradient of an image, well, formally what it is that if you think of images as functions, rather than just matrices, the gradient is just the actual derivatives of that function. So this is something you actually see a lot. I'm trying to avoid as much as I can kind of the notation of images as functions, but you will see it if you ever take a vision course. So it's worth mentioning at least a little bit. I'm calling an image this matrix here, y in R m by n, but you could just easily think about the image is a function, from, really from, R to R to another real valued, so let's say it like this, to 0, 1, where the inputs of this function, so f of x and y, is just the x, y coordinates in your image. That's a little bit odd because we don't actually have the functional form of an image, right? All we have it is evaluated at essentially the integer values of this thing here. And we don't have it anywhere, so if this is negative, we never have it there. And if it's bigger than the bounds of the image, we don't have that. But conceptually, you can think of images like functions like this, right? It's just that we don't observe the whole thing. We only observe a small amount of them. If they are functions, though, you can just take the partial derivatives of this function with respect to the x and the y components. Right, that would essentially be saying, all right, this is outputting a number between 0 and 1. If I have some area here in my image where there is a very light, so this on this side is all 0 and this side is all 1, then the gradient at these points here would be very big, right? Because the gradient here would be saying, in this direction, my function is increasing very rapidly. And so that would mean that d partial x is a lot bigger than 0 at this point in the image, right? Similarly, the same thing goes true for y here, because actually the edge is increasing in both directions, assuming this is the direction of x increasing, this is the direction of y increasing. Now, in reality, we don't have a functional form of an image. We could do things like sort of smooth the image, etc. But as with a lot of computer vision applications, ultimately you want to get down to just sort of real valued or discrete valued operations. You don't want to do things like create a smooth interpolated version of the image and then take operations in that space. You effectively can't be doing that anyway, but what you really want is you just want to do a bunch of multiplications and additions, because those are really fast on a computer, right? So the obvious way to approximate this then, this gradient that we're talking about here, and this is sort of almost too simple to even mention, but it's just to take differences of the image, right? So if you have one pixel here, another pixel there, I'll call this yij plus 1, and this is yij, then, right, d of x is sort of basically just yij plus 1 minus yij. Right? It's just the difference of adjacent pixels. So one way of writing this actually is that the difference is something like a convolution of this very simple operator here with the whole image. Right? We take this thing with -1 and 1, and we convolve it with the whole image, and that is our gradient, our x gradient. This would be the y gradient. Now, caveats being things like, well, people typically don't use even size filters, so it's more common to use this. Not too big of a difference, but just people typically use the average on one side or the other to compute the difference rather than just difference over adjacent pixels. But even getting beyond just that, it turns out if you do just this, you're very susceptible to noise in your image. Right? As you might imagine, little differences, little things like speckle in a camera and stuff like this will cause you to say there's a really big gradient here, and really big gradients everywhere. Right? So what's more common then is to actually do two operations. You first smooth the image, and then you apply your differencing operator. And in fact, it turns out you don't even have to do that, because you can write that joint operation of first smooth with, say, a Gaussian filter, and then apply differencing. You can write that as an independent convolution in and of itself. And this is just something called, it's a single convolution that does both these things. These are called Sobel filters in computer vision. And they can be either 3 by 3 or 5 by 5, depending on the size of your Gaussian blur. They have different sizes, but this is essentially just a better way of computing those gradients. So the practical takeaway from all of this is that to compute a gradient in practice, what you do is you take one of these filters and you convolve it with the image. That is the gradient. That's the only gradient we're ever going to really talk about. Even though the functional gradient is this sort of mathematical quantity, we don't ever really see that. All we ever see is just take these, convolve them with the image. And in fact, because it's so common, actually, I don't have it yet. The next slide. OK, next slide. So what does this actually look like? All right, so it looks, fortunately, like almost exactly what you would expect. So here's our original image. It's like a famous image used for computer vision, too, by the way. I call this cameraman or photographer. I forget what it's called. But you'll see it a lot if you take computer vision courses. We take this image, and we run our Sobel filter over the image. What we get out is this. So this is a very clean image. It's sort of very easy to see this. This would be we would expect this here. There's very, very sharp edges here. So if we take differences, we will very obviously see an edge along those axes. What I'm plotting here is actually the magnitude of the gradient. So I'm computing the gradient using a Sobel filter in both the x and y directions, and then I'm plotting the square root of the sum of those two things squared. So it's sort of the magnitude of the gradients what I'm plotting here. And as you might imagine, this sort of captures the edges in the picture, right? Whenever there's an edge in the original picture, you have a bright spot here. Where there isn't an edge, it's black. And if you just look at this picture here, you really can get a lot of information out of it, right? You can sort of tell what's going on here, even though there is much less information here than there is in the original image. So as with all things, also a OpenCV function to do this. And now let's try this one out. Maybe this one will look a little more normal on this. OK, here is the magnitude of the gradient. So I wore a good shirt today for doing this. Lots of edges in my shirt. And it's kind of what you expect. I mean, you have to sort of imagine what the actual image looks like here. But as you can imagine, right, there's going to be an image around my hair here, right, because the back is much different color and intensity than my hair. There's a lot of images in my shirt, too, because there's lots of white here, and there's lots of darker colors that are very good for image detection. You can see, again, the infinite recursion sort of creating this weird shadow behind me. Turn to the class, see what the class all looks like in edge detection. So nicely looking at all the students there. You have edges around yourselves. A lot of you do. But it looks kind of what you expect, right? From this picture, you can get a lot of information about what's actually happening in an image without, oops. Hit the thing by accident. Oh, there it is. It's just doing this. OK, without looking at the whole image, you can get a lot of information about this, right? About what's happening here. Now, the last thing I'll say in this lecture, before we get to the midterms, is those images are nice, but they're not great. They have some problems too. Namely, these edges span multiple pixels, and they're kind of, what is really an edge here? It's still a grayscale image, right? There's no notion of like this is an edge or not. It's just a grayscale image where we're plotting the magnitude of some quantity. If that's above a threshold, is that an edge then? What makes something an edge? If there's 5 pixels here that correspond to the edge, which one is the actual edge? And which one was just sort of part of the existing edge, right? Especially when you blur it with a Gaussian blur to begin with, you're going to have these edges that look like a lot of different edges. So what do you actually do? And the last step people usually do is essentially do some transformations of this thing and do some operations on it to get something that looks a little bit more like a single edge for each edge we see in the image. And the most popular, or a very popular way of doing this, is called the canny edge detector. I'm not going to describe these in detail. I'm just going to describe kind of intuitively what they're doing here. So there's a couple additions to this gradient that this algorithm does to find sort of more exact notion, a more exact notion of an edge in an image. The first one is something called non-maximal suppression. And it's a little actually hard to implement sometimes. Well, not really, but it's not completely trivial to implement. But intuitively, it's very simple. What it says is, if we have an edge there, and we look at the intensity of the edge kind of perpendicular to the edge itself, it looks something like this, right? So this is sort of a cross section, like in this direction here, showing the intensity in that cross section. And what the Carnegie edge detector does is says, let's ignore all those points except the top one. Just treat that as the pixel that has the edge in it. The rest we throw away. So we suppress everything but the maximum, hence the term non-maximal suppression. Also, very simply, it just throws out any edges that are too small. If it's just a little teeny edge somewhere, it'll just say that isn't worth worrying about. Toss it. And finally, it has, it's actually not quite a complete description, but it ignores edges that don't ever get to a high enough magnitude. But then it also sort of stops them from being an edge once they fall below a certain threshold. So it has an upper and lower threshold that if it never reaches that upper threshold, it is not an edge. But if it never falls below, as soon as it falls below the bottom threshold, that edge is done. But it can go kind of in the middle and still be an edge, but it's not an edge if it's only in the middle, essentially. Yeah?
How do you find the perpendicular direction?
Right. That's a great question. How do you find that? Oops. I went forward instead. How do you find that? You want to guess this?
Divide the two gradients.
Divide the two gradients.
That will give you the tan inverse of the...
Yeah. Or I would even say just those are the gradients. The gradient there is this pointing this way. Right? So if you look at the direction of the gradient, it will be in that direction. So what you do is you actually look at this thing here in the direction of the gradients themselves. Because the gradient, remember, has two components. I'm just drawing the magnitude here. The gradient itself is actually pointing in one way or the other here. They each have a magnitude and a direction. And so you just look in that direction. You can get the tan of it too, but I would just say let's just get the actual gradient direction, which is the gradient. All right. So we do that. It looks like this. So now we have single pixels to trace out all the edges here and do a pretty good job of sort of delineating most of the edges in that image. There certainly are some cases here, like in the grass, where things are kind of funky. It's finding edges here that we know there aren't really edges there truly, but if you look at the lighting, there are edges here. At least more, for example, than this building's side this way. This is actually bigger differences down here in places. So it isn't perfect, but still, you can imagine this is a pretty good representation of what's happening here, right? You could actually do a pretty good job of figuring out what's going on from this image here. And finally, showing what it looks like for me, here is now Carnegie edge detection run on me. So not perfect, but doing a pretty good job of finding like kind of crisp, nice lines, at least in my shirt, around my mouth and face to a certain degree. If I sort of in the right light, I guess I have to be kind of under the lights properly. If I get too close, well, it's working okay actually. There's a lot of noise. If you want to do this kind of in the most robust way possible, this is just doing this independently on each frame. If you want to do it in a more robust way, you might want to do things like track edges over time. And if you keep seeing one, you build some intuition that it stays there. But for kind of a first pass, this isn't too bad, right? This is pretty good. And it is, like everything else, in OpenCV at least, one line of code to actually get this. So that is image processing. And I have 20 minutes left now to talk about the midterm. So yes, we'll go on to the next lecture next time. But for now, let's pause. And actually, we have the midterms to hand back, so we can give them back first. I think we're going to call people up so that you don't pass them out. Or you can just put, yeah, I guess. What's the best way to do this, actually, if we're
Probably you can just call one person at a time.
maybe say on different sides of the room or something like that? Yeah. We can turn off the camera, probably.